Welcome to our deep dive into Norway's glacial seismology. To set the stage, what exactly is cryoseismology, and why has Norway emerged as a global hotspot for this field?
Cryoseismology is the study of seismic signals produced by ice movement, cracking, or meltwater events within glaciers. Norway's unique Arctic and subarctic environments, especially in Svalbard, offer ideal conditions-extensive glacier coverage, and rapid climate-driven changes make it a natural laboratory.
It's fascinating how the landscape shapes research focus. Can you elaborate on how Norway's geography specifically catalyzes innovation in this science?
Absolutely. Norway's high-latitude glaciers, such as those in Spitsbergen, undergo pronounced seasonal transitions. This variability allows researchers to observe seismic activity tied to both long-term climate trends and short-term melt events, providing rich data for global comparisons.
Let's zoom into Svalbard, often called the epicenter of Norwegian cryoseismology. What makes glaciers like Kronbreen, Tunabreen, and Hansbreen so valuable for field studies?
These glaciers are among the most dynamic in the Arctic. They're accessible, experience rapid movement, and regularly calve into fjords. Dense arrays of seismometers like those deployed for the SPICE project capture high-frequency icequakes, providing detailed temporal and spatial data.
How do these seismic networks function in such harsh environments, especially during polar night or extreme cold?
Engineers have developed insulated stations powered by solar panels and batteries. Data is often transmitted via satellite, enabling near real-time monitoring. These innovations are crucial for uninterrupted year-round data collection.
Transitioning to mainland Norway, the west coast and Jostedalsbreen see different glacial dynamics. How does seismic research there differ from Svalbard?
Mainland glaciers are smaller and respond more rapidly to temperature shifts. Here, seismic networks not only monitor ice movement, but also detect glacial lake outburst floods (GLOFs), which can be catastrophic. Seismic signals often precede visible flooding, offering a crucial early warning tool.
Could you clarify how a GLOF is detected seismically, perhaps with an analogy?
Think of the glacier as a dam. When the water pressure builds and the dam breaks, the sudden rush of water generates ground vibrations, much like a mini earthquake. Seismometers pick up these signals, alerting scientists to dangerous outbursts.
Norwegian expertise isn't confined to Norway. What role do Norwegian scientists play in Greenland's seismic research?
Norwegian teams collaborate internationally, especially on Greenland's rapidly melting west coast. They apply seismic techniques honed in Svalbard to study ice flow, basal sliding, and meltwater drainage. This cross-pollination advances glaciology globally, as Greenland's scale and melt rates offer fresh challenges.
Are there noteworthy differences in seismic data between Svalbard and Greenland?
Greenland's ice sheet generates larger, more complex seismic events due to its size. However, many underlying processes like crevasse formation and subglacial floods are analogous, allowing Norwegian-developed methods to be adapted effectively.
Institutional collaboration has been key to Norway's success. Can you highlight the main research centers and their unique contributions?
Certainly. The Norwegian Polar Institute coordinates Svalbard fieldwork and manages crucial data archives. The University of Oslo's SEED excels in seismic modeling, while the University of Bergen focuses on climate-glacier interactions. UNIS in Longyearbyen serves as a vital field and educational hub, training the next generation.
How do these centers synergize, especially with overlapping research agendas?
They share field data, co-author studies, and often run joint expeditions. This collaborative model ensures that expertise in instrumentation, modeling, and climate science is fully integrated, maximizing research impact.
Moving to the human element, the field boasts several influential figures. Who stands out among Norway's glacial seismologists, and how have they shaped the discipline?
Prof. Natalie Barlow pioneered methodologies for interpreting seismicity in Svalbard, while Dr. Anders Schomaker is renowned for his work on GLOFs using seismic data. Meanwhile, Prof. Natalie Barlow, plus class, odd.node-atation. Karen Andreasen's marine geophysics has illuminated subglacial processes, and Professor Yasmina Stanton's modeling has deepened our understanding of ice physics.
What about emerging researchers show is the torch being passed?
Dozens of postdocs and PhD candidates at UIO, NPI, UIB, and UNIS are advancing the field, often blending seismic methods with satellite and drone data for multi-scale insights.
Let's dive deeper into technical breakthroughs. How has seismic source modeling evolved in Norwegian research?
Early models treated glacier quakes as simple point sources. Today, Norwegian teams use complex algorithms that simulate distributed ruptures along crevasses or basal slip plains. This shift enables more accurate interpretations of ice dynamics, as shown in Stanton et al. Recent publications.
How do these models handle the ambiguity between natural earthquakes and glacial seismicity?
Advanced pattern recognition, including machine learning, discerns ice quakes from tectonic events. Parameters like frequency content, duration, and waveform shape are analyzed. Glacial events tend to have lower frequencies and longer durations than classic earthquakes.
Let's transition to interdisciplinary research. How is seismic data integrated with climate and oceanographic studies in Norway?
Seismicity often spikes during melt seasons, correlating with temperature and precipitation data. Institutions like UIB's Bjørknes Center use this synergy to model feedbacks between ocean currents, air temperature, and glacier stability, revealing how warming oceans accelerate under ice melting.
Can you provide a real-world example of such integration?
Recent studies linked increases in submarine seismicity to warm Atlantic water intruding beneath Svalbard glaciers, highlighting a direct ocean seismic interaction with profound implications for sea level rise projections.
Despite progress, the field faces considerable challenges. What are the biggest obstacles for Norwegian cryoseismologists today?
Data scarcity remains a hurdle, especially during harsh winter months or remote locations. Equipment maintenance is difficult in 30°C conditions, and limited funding restricts network expansion. Moreover, with climate change accelerating, keeping pace with rapidly evolving glacier behavior is a constant race.
How are researchers addressing these challenges, perhaps with emerging technologies?
Innovations like autonomous drones for sensor deployment and AI-driven data analysis are helping. There's also a push for open data sharing across Arctic nations, which could exponentially increase observational coverage and scientific return.
Finally, let's discuss knowledge dissemination. With few textbooks and most knowledge in articles, how do Norwegian researchers ensure the field's growth and public engagement?
Academic articles, like Podolsky, Walter's Review, serve as foundational references. Norwegian teams publish in top journals and participate in open access initiatives. Educational programs at UNIS and outreach via public talks and documentaries are also key for inspiring new scientists and informing policy.
What's the outlook for expanding cryoseismology's impact beyond academia?
As glacial hazards become more pressing, collaborations with emergency planners and policymakers are increasing. Seismic monitoring is now seen not just as academic, but as essential for Arctic community resilience and climate adaptation strategies.